Hello. Can people hear me?
Yeah, I can hear you.
Okay, good. Oh. Just a second. Something's wrong with my camera.
Okay, so now you should be able to see me and hear me. If that is not the case, please let me know. Right, okay, so today an exciting topic, series. Please tell me if you have done arithmetic and geometric series in school, sequences, arithmetic sequences in school. One for yes, 0 for no. Yes, good. Taught it to myself. Good. Started it today. Not excellent. Okay. Right. So a few people know. Lots of yeses. What about Taylor? The Maclaurin series. Has anyone done Maclaurin series? Good. Oh, Alistair, brilliant. So it looks like in Scotland they teach stuff. Okay. Okay, so today I'm going to talk about three things. So arithmetic series, well, series in general, geometric series, and Taylor series. Okay, so you learned ahead by yourself. Okay, that's good. That's good. So let's start. I meant they teach the good stuff. Right. Okay, so it's just a warm-up for you. So what is the next term in the following sequence? So let's start with the first one. So give me some ideas. If you know it, it would be unfair to others. So just keep silent if you know these sequences. If you don't know, give it a go. So what is the next term in the sequence? 1, 11, 21, 1211, 111,221. That's a lot. 312,000. So Alfie says 312211, but that's this one. You think this is the next one is the same as this one? Would you be able to explain, Alfie? Oh, okay. Something to do with the digits, yes, of course. One, one, one. So Amanda says 111321. 1, 1, 1, 1, 3, 2, 1, 3, 2, 1, 1. 1, 1. Good. Yes, Amanda, you are correct. How did you figure it out? Would you like to explain? Say what you see. Exactly. You just say what you see. So this is an interesting sequence. So it's not really mathematical. It's more like a child sequence. So first it's 1, 1. So it's one digit 1. So we write 1, 1. Now the next one contains 2 1s. So we say 2 1s. Now the next one, 1, 2, and 2, 1. 1, 2, and 1, 1. So 1, 2, and 1, 1. The next one is 1, 1, 1, 2, and 2 1s. The next one is 3 1s, so 3 1s, 1, 2, 2 2s, so 2 2s, and 1 1. Okay, the next one, does everyone understand it? If you don't understand it, type 0, please. If you do understand it, one. Yeah, so you just say what you see. Okay. So this is 1 3, 1 1, 2 2s, and 2 1s. Okay, good. The next sequence. Has anyone figured it out? As with the first sequence, this sequence is very easily done by children. Down arrow. Ooh, Hadrahad. Yes. Yes, well done. It is. Now, if you want to figure out a sequence, well, you need to look at like what do they have in common? Well, they all have a vertical line of symmetry. All these lines, they all have a vertical line of symmetry. And if we just look at the left-hand side of each shape, what do we notice? It's 1, 2, 3, 4, 5, and the next shape is 6. So write 6, and then we mirror it. Okay, so very simple, like but a bit unusual. I would say. I'd say I saw this sequence when I was 20, and I was really struggling with it. Honestly, I don't think I got it because I was looking at how do we move the matchsticks with rotations. I tried everything, and I couldn't figure it out. Oh, this one. These shapes, if you look at the first half, just the left half of this image looks like this. If you look at the first half of this, it looks like this. If you look at the first, this looks like this. So 1, 2, 3, 4, 5, and then it's just mirrored. How many formulas for a sequence which has the first terms 1, 2, 3, 4, 5? So give me a formula. Give me a formula. That has this. N. Yeah, very good. If the formula is n, if un is n, then the sequence is 1, 2, 3, 4, 5, etc. But could it be a different formula? You can guess the answer. You can guess the answer. How many formulas does it have? How many formulas do you think it has? Probably infinite, Alistair, you're correct. Infinite. The question is phrased like it is infinite. So what can it be? What can it be? Can you give me a... Okay, so what do you mean by defined polynomials, Alfie? Can the formula simplify back to n? Well, no, that won't work. That won't work. Because, for example, if you write 3 plus n minus 3, well, it's the same formula as it's this formula. So it's not really. For all we know, the sixth term could be 34. Absolutely, yeah, it could be anything. We don't know. There could be infinitely many, and we can write a formula which looks like this, for example. Un is equal n plus, and something that is equal to 0 when n is 1, 2, 3, 4, or 5. So, like this, for example. This would be a good example. N minus 1, n minus 2, n minus 3, n minus 4, and n minus 5, multiplied by a something. Let's call it Fn. Now, this thing is 0 when equals to 0 when n is 1, 2, 3, 4, 5. Yeah, for any value of for any of those values, 1, 2, 3, 4, or 5, this is 0. And then n plus n, so that makes it 1, 2, 3, 4, 5. But the next number could be absolutely anything, because Fn can be absolutely anything. Right? So Fn could be 1, for example, and then the next number would be 1, 2, 3, 4, 5, and the next number would be 6 minus 1, so that's 5, 4, 3, 2, 1, which is 120, I believe. So it's going to be 126. Right? So the next in this sequence, the sixth number would be 126. And if this could be sine n, and then you get a completely different sequence, which goes off 1, 2, 3, 4, 5, and then abracadabra. So yeah. So the message here is that if you look at the first 5 terms and you think you see a sequence, well, it's not necessarily that way. It doesn't have to be that way. It could be infinitely many possibilities. In fact, there could be infinitely many possibilities with, if you're given the first 10 terms or the first 20 terms, you could think of anything. Right. Okay. Moving on. The partial sum of a sequence is defined as. the partial sum of the sequence. Find the formula for the sequence if Sn is equal to n cubed. So partial sum of a sequence. So basically, what does it mean? Well, it's the sum of the first n terms. That's the sum of first n terms. This is quite an unusual problem because you're given the formula for the sequence and then you're asked to find the formula for the first n terms. Here it's the other way around. But we can devise a method. So who thinks they can find the first term, A1? What's A1? I'm not sure that everyone understands what I'm talking about. So I'll just clarify things. The sum of AI, where I from 1 to n. So it's A1 plus A2 plus A3 plus AN. Is everyone clear on that? That Sn is A1 plus A2 plus A3. Okay. Yeah, so S1, yeah, very good. S1 is going to be 1 cubed. Yes, 1 cubed. So it's 1. And S1 is A1. So A1 is 1. Now S2 is A1 plus A2. And that's equal to 2 cubed, which is 8. Can we work out A2? A2 is 7. Absolutely. S3 is A1 plus A2 plus A3. And that's equal to what is it equal to? 3 cubed, which is 27. 27. Therefore, A3 is 19. Okay, well, I can't really tell what's the sequence. We are adding 6, then we are adding 12. Okay, well, yes, I can see that sequence. So A4. So S4 is A1 plus A2 plus A3 plus A4 is 64. So that makes it, what does it make it? 64 minus 27, 37? 37. Okay. And we need to find the formula for AN. For AN. It's 1, so it's plus 6. This is plus 12. This is plus 18. Okay. I honestly forgot how to work it out. It's going to be a quadratic sequence. Okay. a situation. I forgot how to work out the sequence, so I'm inventing a way how to do it. So what do I know? What I know that A1 is 1, so the next one is A2. So I'm thinking, my conjecture is that AN is a quadratic. So it's going to be something n squared. So for simplicity, alpha n squared plus beta n plus gamma. Yeah, so alpha, beta, and gamma are the things that I need to find. So this is the unknown formula for the nth term. So what do I know? I know that A1 is 1. Would that help me? Yes. I know that A1 is alpha plus beta plus gamma, and that's equal to 1. Then I'm using A2. A2 is 7, so that's 4 alpha plus 2 beta plus gamma is equal to 7. A3 is 9 alpha plus 3 beta plus gamma is equal to 19. Okay, so subtracting the first two equations. So I'm doing this minus this. So I get 3 alpha plus beta is equal to 6. And subtracting the, what do I want? Well, subtracting the these ones, I get 8 alpha plus 2 beta equals 18. So I divide the second one by 2, I get 4 alpha plus beta equals 9. And if you are attentive, you can work out alpha is n cubed minus n minus 1 cubed. Yeah, the common difference is dependent on the term. It might be, Victoria, you might be right. Alpha is 3. Beta is well, we can work out beta. It's 3, 9 minus 3 minus 3, and gamma 3 minus 3, gamma is 1. So the formula AN is 3n squared, yes, minus 3n plus 1. So let's see if it works. 3n squared with sorry, 1 works, 2 won't work. Well, we need to check, will 4 work? 3 times 60 is 16 minus 12 plus 1, and that is 30. That's at 37. Doesn't read. Oh, that's S. Yes, 37. Of course. Yes, before is 37. So the formula is 3n squared minus 3n plus 1. So we worked out the formula. So I didn't tell you how I worked out that it's going to be a quadratic, but if you look at the quadratic sequence, it behaves the same way. If you look at the 1, 4, 9, 16 is plus 3 plus 5 plus plus 7. So if the common difference, sorry, if the difference is not a common difference because it's no longer common, if the difference is an arithmetic sequence, that means the sequence itself is a quadratic sequence. So I've written out a quadratic sequence with unknown coefficients, and I worked out alpha, beta, and gamma. There's a shortcut to it, and in some schools they teach it. I honestly forgot the shortcut. So this is the way I would do it. Does that make sense? Have I is someone utterly confused? How much sense does it make on a scale of 0 to 10, please? Okay, lots of tens. Lots of tens and shy sixes, or just lots of tens? I hope for the latter. 19 people in the chat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 8 silent people. Silent people, would you vote, please? Okay. Right. Any questions? Any questions? Anything you don't understand? Ultimately, what we did, we went from a formula for the sum to the formula for the nth term. Okay, the formula for the nth term. You should know this very well from GCSE. Formula for the nth term of a sequence. That should be very common for you. Right. Now the next problem is a very common thing. So if you know the properties of an arithmetic sequence, you'll be able to do it relatively easy. Relatively easy. So let's have a look. So what do we have? The sum of the first and fifth term of an arithmetic sequence. So we need a way of writing an arithmetic sequence. Well, we know that an arithmetic sequence goes, you start with a number, let's say A. The next number is A plus D. Where D, we say it's a common difference. The next number is going to be A plus 2D. 2D. The next number is going to be A plus 3D. So you always add the same number to it. So you start with A, then it's A plus D, then it's A plus D plus D. So that's an arithmetic sequence by definition. Therefore, yes, correct, Alistair, yes, the nth term of an arithmetic sequence is going to be A plus n minus 1 D. N minus 1 because the first one is, for the first one, we add 0 times. For the second time, we add once. For the third term, we add twice, etc. So it's always one less than the number of the term. So the first term is A. The fifth term is A plus 4D. A plus 4D. So this is A1 plus A5. That's that. And that's equal to 5/3. And then the product of the third and fourth is 60. So the product of the third multiplied by the fourth, that's A plus 2D multiplied by A plus 3D. And that's equal to 6572. Well, what would you do here? What would you do here? It is simultaneous equations. But it looks kind of horrible. A plus 2d is 5, 6. Ooh, yes, Anusha, very good. You saw it. Like an unexperienced student would expand the brackets in the bottom and then deal with a very nasty quadratic. But if you notice that a plus 4d is very similar to a plus 2d, yes, you will see that it is 2a plus 4d, and it's equal to 5/3. Well, we could divide by 2, and we would get a plus 2d equals to 5/6. Well done. But when yes, Alistair, that is correct, but we're not looking for the sum. Oh, we are looking for the sum. Sorry, we need to find a and d first. Yes, sorry. Yes, so right now we are looking for the a and d, and we can see that a plus d is 5/6, and we can sub that into here. So 5/6 multiplied by a plus 3d is equal to 65/70 seconds. Divide by 5, that's 13. Yes, 13, and this divisible by, is it 72 divided by 2 is 36, and divided by 3 is 12, so 12. Good, so we have a plus 3d is equal to 13/12, and we have a plus 2d. 2d is equal to 5/6, which we can immediately write as 10/6. Therefore, we subtract and we get d is equal to 3/6. So 3/10/12. Sorry, 3/12. So that's a quarter. And a is 2 quarters. 5/6 minus a half is 5/6 minus a half, which is, it does look like it's 1/3. 2/6, which is 1/3. Yes. And then the sum of the first 17 terms, there's a formula for that. And I hope you know how to derive that formula. It's done so many times that I don't feel I need to do it here, but make sure you know how to derive this formula. Sn is equal to 2a plus n minus 1d divided over 2 and multiplied by n. So the sum of the first 17 terms is 2 multiplied by the first term, which is 1/3, plus n minus 1, which is 16 multiplied by a quarter, divided by 2 and multiplied by 17. So 2/3 plus 4. 2/3 plus 4, which is 1/3 plus 2 multiplied by 17. So I divided by 2 just to make life easier. So 2.5 times 17. So that's 34 plus 8.5. That's 42.5. 42.5. I'll double check on my calculator. 2.5 times 17. Yes, I haven't lost it. Okay. The sum of an arithmetic sequence. So do study that. I mean, it's not a very difficult formula, and it's a lot of fun. It's a third, yes. Yeah, it's a third plus 2. So 2 and 1/3. Okay, so it's not that simple. That's what? 3, 6, 7. 7 times 17. 7 times 17 is 119 thirds. I think that's it. What is the formula for timesing arithmetic sequence? Oh, you mean a product? Product of an arithmetic sequence. I don't know. There might be. I've never used it. Never used the formula for the product of an arithmetic sequence. Yeah, sorry. So I wouldn't know that. But something is something I'd like to explore when I have some time. Okay. I'm a bit of a practical mathematician. I really enjoy physics, and I use the maths to help me with the physics. I enjoy the beauty of pure maths. Is not always my cup of tea when you just maths for the sake of maths. I like it when maths is applied to something. Okay, solve the equation, and it looks weird. Have you ever seen equations with infinitely many terms? What is the result for the sum of all natural numbers being minus 1/12? Is it the sum of the natural numbers, though? Just give me a minute. So, yes, the Ramanujan summation, and Here you go. Here's a link where you can explore this further. Okay. It's the Ramanujan summation. Okay. This one. So this is an equation with infinitely many terms. But you would notice that these form a geometric sequence. This is a geometric sequence. And because x is less than 1, so let's explore this sequence further. So we have x squared minus x cubed plus x to the power 4 minus x to the power 5 plus etc. We could use the standard result for the formula, but I want to do it differently. I notice that the whole thing is this in each step you're multiplied by minus x. So in each step you're multiplied by minus x. So let's suppose that we have the first I'm trying to okay, let's suppose that this thing is equal to n. We're taking the first, it's etc plus, because we start with x squared. Well, let's say we end with x to the power n plus 1. Okay. Probably, yeah. Alistair, might be true. So suppose we take the first n. Yes, so we're not taking the infinity, but let's say there are n terms. Take the n. Then we multiply this by minus x. So minus x Sn is going to be equal to minus x cubed plus x to the power 4 minus x to the power 5 plus etc. And then it's going to be, the last one is going to be minus x to the power n plus 2. And then what we do, we subtract this minus this, and we get Sn 1 minus x, or 1 plus x, is equal to x squared, and then this cancels, they all cancel except the last one. And because we're subtracting, it's going to be plus x to the power n plus 2. So Sn is equal to x squared plus x to the power n plus 2 divided by 1 plus x. Okay. Now we need the limit, because we need n goes to infinity. The limit as n tends to infinity of Sn, and it's going to be x squared plus, it's going to be the limit of n tends to 0, x squared plus x to the power n plus 2, 1 plus x. The only thing that changes as n tends to infinity is this term. because everything else is fixed. It's x. It doesn't depend on n. Now, x to the power n plus 2, because x is less than 1, this tends to 0. Does that make sense? Please tell me how much sense does it make on a scale of 0 to 10. X is less than 1. Because it's a number less than 1, and you're multiplying it by itself, therefore it tends to 0. So the sum to infinity is in fact x squared divided by 1 plus x. S to infinity. So I achieved this by writing out what Sn is. Then I multiplied by minus x, and I subtracted the 2, and I got this expression. Then I simplified it, made it limit to n equals n to infinity, and sorry, to infinity, and this tends to 0. Now, we also have a formula which you will find in any A-level book, any high school book, that the sum to infinity of an infinite geometric series is the first term divided by 1 minus the common ratio. But this only works if the common ratio is less than 1. And incidentally, for this sequence, the first term is x squared, and the common ratio is minus x. Therefore, the sum to infinity is equal to the first term, x squared, divided by 1 plus x. 1 minus r. That's the sum for the first n terms. The sum. So let's say you have a geometric sequence. A geometric sequence is a first term. The next term is going to be AR. The next term is AR squared plus etc. And if you have n terms, the last term is going to be AR to the power n minus 1. And we call this the Sn, the partial sum, or the sum of the first n terms. And that is equal to A multiplied by R to the power n minus 1 divided by R minus 1. But Rn tends to 0. Yes, if R is less than 1, then sum to infinity is equal to A plus AR plus AR squared plus to infinity is equal to the limit of this, and this becomes 0. This becomes 0, and you have minus, so you get A. If you simplify this, you get 1 minus R. Because this becomes minus 1, so that's minus A divided by R minus 1, which is the same as A over R, 1 minus R. Okay. So that's sum to infinity. And the sum of the first n terms. Right, so we can safely rewrite this equation. And choose a different color. So 2x plus 1 plus x squared over 1 plus x is equal to 13 over 6. And then it's just a boring quadratic equation. Okay. I hope you know you can solve quadratics. So it's going to be 2x plus 1 multiplied by 1 plus x plus x squared. 6 equals 13. 1 plus x. And I'm sure you can do it. Okay. Right. The next is another geometric sequence, a geometric series, and it's probably one of the most important geometric series in your lives, okay? Because at some point, most of you, the majority of you, will have to deal with this. A mortgage is a geometric series. So let's have a look. Brian takes out a mortgage, and at the end for £300,000, which is a normal mortgage. I myself took a mortgage of 315,000 this year, and now I am a slave to the bank, basically. Anyways, £300,000 mortgage. At the end of each year, 5% gets added to the debt. And after this, Brian pays an installment of £30,000. So what happens? So Brian has £300,000 of debt. So this is the money that he owes the bank. Now a year goes by, and after a year, so this is 0 years. 1 year, he gets this debt increases by 5%. So 300,000 times 1.05, 300,000 times 1.05, yeah, because you're increasing by 5%, and that makes it £315,000. Now, not exactly, because the banks don't let you do that. If you do this after 20 years, you will owe the bank 300,000 times 1.05 to the power of 20. You will owe the bank £800,000, which you probably won't be able to afford to pay back. So banks don't like it. Banks ask you to pay back some of the money. And so the Brian pays £30,000, and he receives, okay, that's a bad way of writing it. Just put an arrow here. £285,000. £285,000. That's his debt. Okay, so his debt goes back down by 15,000 after 1 year. He's paid off £30,000, but because interest gets added and then he pays the money, he now owes the bank £285,000. What would happen in year 2? In year 2, well, the same thing. We have the money, 285,000, 285,000 increases by 5%, 0.5, and then subtracting 30,000. Subtracting 30,000, and we get Alistair, short answer is no. Yes, the money that you pay will be multiplied by 1.05 as well. So it's not that formula. And that gives you 285,000 multiplied by 1.05 minus 30,000 pounds. That's 69,250. So the debt goes down by more than 15,000 in the second year. That makes sense. You owe less money to the bank, so less money gets added as interest. But because you pay the same amount every year, that's your well, let's work this out. No, it's not. So and so on and so on until the money is zero. Okay, so you want to know how many years will the debt equal to zero. So let's start. So let's say M is the initial amount of money. And M1 is the MN is the after n years. We'll have the percent rate. This is the rate, which is in this case 1.05. This number, and then D is the deposit, is the money that you pay every year at the end of the year. D is 30,000 pounds. Because we want a general formula. We're not interested in Brian. Yes, Brian might be a wonderful person, but we're interested in the general form. So we know that M1 is the initial amount of money multiplied by by R, multiplied by R minus D. M2 is the whole thing multiplied by R is the money one multiplied by R, so that's M R minus D multiplied by R. So we multiply the whole amount by R, and then we subtract D. And we can simplify this, and we can see that it is MR squared minus DR minus D. Similarly, M3 is going to be MR cubed minus dr squared minus dr minus d. So you could generalize Mn is mrn minus d multiplied by 1 plus r plus etc. plus r n minus 1. Okay, is everyone happy with that formula? From 1 to 10, please. Are you happy with this formula? 14. So why 9? Why not 10? So for those who put 9. concise way of writing the last part? Well, you can use the sigma notation. Yes, you can write something like sigma r to the power I from I equals 0 to n minus 1. It doesn't really help in this particular case. But the thing is that it is a geometric sequence. It is a geometric sequence, and we know that the sum of the geometric sequence, the sum of the first n terms, and well, the first n terms is the first term multiplied by the r to the power n minus 1 divided by r minus 1. Therefore, this thing is going to be equal, the first term is 1 multiplied by r to the power n minus 1 divided by r minus 1. So that's pretty much that. And it's multiplied by d, so you can write down d. All right, so the amount of money after n years, the amount of money that you owe the bank after n years is going to be MRN minus the yearly deposit, and r to the power n minus 1 divided by r minus 1. Now, we want to know when this is 0, when the amount of money that you owe the bank is 0. Therefore, we multiply by r minus 1, so it's r minus 1 multiplied by mRn equals d rn minus 1. And so you divide that by, oh, we need to open the brackets, of course. So rm rn minus mRn equals drn minus d. There's an easier way of doing it, but let's do it this way. We want to find n, so that means we have rn open bracket rm minus m minus d equals minus d. So rn is equal to minus d divided by rm minus m minus d. And it does make sense in a way. We, like, after doing a bunch of calculations, we can do some what we call a sanity check. Does this value make sense? And how do we do that? Well, we see when do we have a singularity here? When do we have a division by 0? So we have if we have rm minus m minus d is 0. What happens? What happens if this is 0? And we have a look, and we say that if the deposit, if d is equal to rm minus You don't pay your debt and there's no interest. Not necessarily, no. So in our scenario, in our case, this is equal to R 105 times 300,000 minus M, so 1.05 minus 1 times 300,000. 300,000. That's equal to 15,000. 15,000. This is the situation where your deposit is 15,000. So let's go back. Let's see what happens if your deposit is 15,000. Your debt increases by 15,000 to 350,000. You pay 15,000 and your debt goes back down to 300,000. That means you are not paying off any debt. Your debt is constant. That means it will take you infinity years to pay out. That means if D is £15,000, infinity years to pay off. Well, if it's less than 15,000, you will never pay off, of course, and that means and this is a situation where Rn is going to be negative, and R to the power n is less than 0, which is not possible. Therefore, there are no solutions. There's no year after the money is so the equation has no, you don't have a singularity, but the equation has no solution if D is less than 15,000. So the 15,000 is the minimum amount you have to pay in order to keep your debt at a constant level. And how do we do this? Well, we use logarithms. So n is a logarithm base R of this expression minus D over Rm minus M minus D. And you can work it out using your calculator. That it would be 14.2 years, I believe. 14.2 years. Yeah, so it's log 30,000 divided by 1.05, etc. Interestingly, this is log base 1.05 of D, which is 30,000 pounds. 30,000 pounds divided by, so this is RM, so that's 15,000 minus 30, so it's 15,000 pounds. 15,000 pounds. And this can be written as log 30,000 pounds minus log 15,000 pounds divided by log 1.05, which is in a way beautiful, because this is the amount of money you pay. This is the minimum amount of money you need to pay to not increase your debt. If you just pay off the percentage, and this divided by this, and this gives you the number of years. So quite an elegant formula, if you ask me. But anyways, the answer is 14.2 years. And as I said, we could do it simpler. Let's look at Desmos. So what I did is I said, so I've put this formula into Desmos. This formula. And I'm looking where it is equal to 0. And here it is. This is the formula. This is the formula. So it's MR. So I'm going to share this with you, so you can play around with it. Okay. And so what can you do here? Well, you can see that after 14.2 years, the debt becomes 0. So this is the amount of debt throughout the years. So let's increase the percent rate to 6%. And now you see it will take 15.7 years to pay off the debt. If you reduce the payment to, let's say, 20,000, it will take 39 years to pay off the debt. Okay, so this is quite an interesting formula. And if you go to a mortgage calculator, for example, I've used this one. Start mortgage calculator, and you say, okay, I want to buy a property for 300,000 with 0 deposit. This is not possible usually. And your mortgage interest rate is 5%, and mortgage term is 14 years. And yeah, and your monthly payment is 24.86. If you multiply this by 12, you get approximately you'll get approximately 30,000 pounds. Okay. How long will you pay for yours? I will pay for mine for 30 years. But I plan to pay more. So if you pay more than the minimum payment, it will take much less time to pay off. So it reduces the time. The thing is that initially you pay the percent, you pay the interest first, and then you go down. Okay, so that's that. 30 years, that's crazy. Absolutely. Okay. So I hope that clears things up, and you can modify this. So this is your handmade mortgage calculator. You can use it. I wonder what happens if I put the other formula. So y is equal to, okay, I'll put another formula. Y is equal to the logarithm of minus d bracket Rm minus m minus d, Rm minus m minus d, multiply d close bracket divided by log 1.05. 30. Well, it just calculates. It just says 14.2. Nothing else. It just gives you a value. And if you say if you reduce D to 15,000, Y becomes undefined. So Y is the number of years. If you reduce the payment, this just becomes straight. You always owe the bank £300,000, and that's it. What would be X instead of Y? Oh, you could say, why not? Yes, and then you can. Oh, yeah, that makes more sense. So 30,000, pay 30,000, and then yeah, the blue line shows you where your debt becomes zero. So if you increase the percent rate, you need to pay off more. 1.05. Step 0.01. 1, 2. Let's see. 1.06 takes more time, etc. The y-axis is scaled very high. What do you mean? When you download it, when you use the link. Okay, so a few fun stuff at the end. Taylor series. So we are going into a wacky world where we are saying that EX is a polynomial. Oh, I see. Yes. That EX is a polynomial. Like how? But EX is not a polynomial by all means. EX is e to the power x. It's a function which has nothing to do with a polynomial, or has it? So apparently you could write EX as a polynomial, as an infinite polynomial. So let's show that it is in fact true. Let's see that we can do this. So how would you find A0? How would you find A0? So this is a polynomial, and we need to find A0, A1, A2, A3. Substitute x equals 0. Thank you, Alfie. That is exactly correct. So this substitute x equals 0. Now, and if we do that, we have e to the power 0 equals A0 plus, well, you can see that this is going to be 0. Therefore, A0 is 1. Because e to the power 0 is 1. And because anything to the power 0 is 1. Okay, so what do we do next? How would we find A1, for example? What can we do? We can differentiate. We differentiate both sides, And luckily for us, the derivative of e to the power x is e to the power x. So we have e to the power x is equal to a1 plus 2a2x plus 3a3x squared plus etc. And we substitute x equals 0 again, and we get e to the power 0 is equal to a1. Therefore, a1 plus 0, because all these terms become 0, that means a1 is also 1. Then we differentiate again, and we get e to the power x is equal to 2a2 plus 3 times 2 times a3x plus etc. We substitute x equals 0 again. We get e to the power 0, and therefore a2 is equal to half. Is everyone on board so far? Especially those who haven't done this before. Anyone not on board? Anyone confused? Please let me know. We differentiate, and then we substitute x equals 0. When we differentiate, a1 goes away. In a similar way, we will see that a3, so we differentiate it again, and we get 3 times 2 times a3 plus 4 times 3 times 2 a4, etc. So we get a3 is 1 divided by 2 times 3, and a4 in a similar way you can show that it's 1 divided by 2 times 3 times 4, which this is, and as a matter of fact, this is 1 over 2 factorial, this is 1 over 3 factorial, and this is 1 over 4 factorial. And we can write out this as e to the power x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus etc. plus xn to the power divided by n factorial plus etc. So it's an infinite set. And let's see. Yes, you can say that. You can write it out as e to the power x is the sum from 0 to infinity of x to the power n divided by n factorial. I think that works. Yeah, that definitely works. Let's show that it is in fact true. So I'm going to remove those. We don't need that. Oh, yeah, we'll probably need another one. Okay. So let's write y equals e to the power x. That's our original function. And let's write down y is equal to 1 plus x. ooh, you can see that they are similar. By subbing in one, does you get the exact value for E? You do, but you have to sub it infinitely many times. So yes. So 1 plus x, and you can see that the two graphs are similar in a small part here. And then you can do plus x squared over 2. Ooh, look at that. The graph becomes, they get closer and closer. Plus x cubed over 3 factorial. And you can see that the graphs get closer and closer and closer. Plus 4 divided by 4 factorial. And so on and so on and so on. Yeah, very good. Nice. Lots of excellent ideas. Absolutely. Yes, you can use 1 plus 1 over n to the power n to approximate e. You can also use this to approximate e. You just sub x equals 1. So when x equals 1, e is approximately 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus etc. Okay, that's an approximation for e. Because it's an approximation because you can't do it infinitely. Yeah, you can't do an infinite sum. But at some point, you just say that it's good enough. It's good enough for my purpose. Therefore, actually, why did I delete that? Yeah, that's perfectly acceptable. Okay. So what we got that the function, this function that the polynomial, this polynomial behaves like this, behaves like e to the power x in the vicinity of vicinity. Okay, in the vicinity of x equals 0, and we call this the Maclaurin expansion. Yes, it's a Maclaurin expansion of e to the power x. So you can approximate pi by using the Maclaurin inverse trig function and then substitute the approximate number. Yes, you can. You can. Now, why is this significant? Well, as a matter of fact, it is very, very significant. So Taylor and Maclaurin they said, so the Maclaurin expansion. The difference between Maclaurin and Taylor series is that the Maclaurin is in the vicinity of 0. That Maclaurin series. Any continuous and infinitely differentiable function I guess so, yes. Probably, but I don't know for sure. Maclaurin series Or oh, that's a statement. Okay, yes. All right. That is cool. That any function, any continuous infinitely differentiable, that means differentiable infinity many times, infinitely, we call it infinitely smooth, infinitely differentiable function can be approximated by, so f of x, any function, can be approximated by the value f0 of the function plus the derivative of that function at the point 0 divided by 1 factorial multiplied by x plus the second derivative of the function at that point divided by 2 factorial and x squared plus the third derivative at point 0 divided by 3 factorial x cubed, etc. Let's try to make sense of this. Let's say f of x is sine x. So f prime, the derivative, is is cos x. F double prime x is minus sine x. F triple prime of x is equal to, well, I'm not really interested in, because I'm interested in the point 0. 0, 0, 0, 0, minus cos x. So sine 0 is 0. Cos 0 is 1. Minus sine 0 is 0. Minus cos x is minus 1. All right. So sine x can be approximated by writing f of 0, that's 0, plus f prime, which is 1, so it's 1x squared, so it's 1x, plus f double prime 0. F triple prime is minus 1, so it's minus x cubed over 3 factorial. Now, if we continue the pattern, f fourth derivative of 0 is sine x 0. The fifth derivative is, and then the cycle repeats again. So 0, 1, 0, minus 1, 0, 1, 0, minus 1. So it's cos x, and that's equal to 1. So it's going to be plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial plus etc. So we remove the zeros. We get an approximation for sine x. And it is really difficult to overestimate the significance of this. Okay. It's really difficult to overestimate the significance of this. Let's see how it works. So y is equal to sine x. So that's sine x. No surprises there. Let's write y equals, so it's 0. So x minus, did I make a mistake? No, x minus x cubed over 3 factorial. Ooh, look at that. A cubic graph which looks very much like the sine in the vicinity of 0. So when close to 0, remember small angle approximation. That is the small angle approximation. We can say that the x minus x cubed over 3 factorial behaves like that. Then we get plus x to the power 5 over 5 factorial, and it gets even closer. And then the next approximation is x to the power 7 over 7 factorial. So give it a go. Give it a go, and try to carry on this approximation. You will see that it gets closer and closer and closer to, it gets a better and better and better approximation of sine. And one more thing is that sine is an odd function. Sine is an odd function, and you can see that it's only odd powers of x. Finally, one thing, why is this so significant? Because of that. Because of your calculator. When you ask your calculator, what is the sine of 23 degrees? How does the calculator know? How does the calculator know the sine of 23 degrees? Does it have a table of values? Does the calculator draw a triangle with 23 degrees and measures the opposite and the hypotenuse? No, the calculator, that is beyond the scope of the work of a calculator. The calculator can only add, subtract, multiply, and divide. These are the only operations the calculator can do as a machine. If you study computer science, you understand that the machine cannot do a sine. It cannot draw a triangle and work out the angles. No, it can't do that. What the calculator knows, that sine is approximately this. And what it does, it substitutes the value for x into that polynomial, and then it gives you your sine of 23. Okay, so the Maclaurin and Taylor series allows machines to do calculations with trigonometric functions, or for calculating e to the power something, or anything like that. The calculators work on Taylor expansions and all machines. So this is the significance of that. We will continue in 2 weeks because I think the assignment is due in the end of February. So we have one more maths webinar, or at least I'll do some more Taylor expansions in the next 2 weeks. All right. See you, everyone. See you. We went over time a bit, yeah, welcome. See you. Have a great week.